Our universe is vast and mysterious. We've made strides in understanding its origins, but fundamental questions remain unanswered. Dark matter and dark energy are key to these mysteries. The familiar matter we see is only a tiny fraction. The rest is shrouded in darkness. This dark sector holds profound mysteries. Dark matter and dark energy are inferred from their effects. They present exciting frontiers in cosmology. Join Ed Isler as we explore these cosmic enigmas. The story of dark matter begins with a gravitational anomaly. Astronomers studying the rotation of galaxies in the 1930s noticed something peculiar. The stars in these galaxies were moving faster than they should have been based on the visible matter alone. This observation implied that there must be some unseen mass lurking in and around galaxies, providing the extra gravitational pull to keep the stars from flying apart. This unseen mass came to be known as dark matter. Further evidence for dark matter came from the study of gravitational lensing. This phenomenon occurs when the gravity of a massive object such as a galaxy cluster bends the path of light from more distant objects behind it. The amount of lensing observed in galaxy clusters far exceeds what can be explained by the visible matter alone. These observations, along with others, have led scientists to believe that dark matter makes up about 85% of the total matter in the universe. Understanding its nature is crucial to understanding the formation and evolution of galaxies and the universe as a whole. The rotational speeds of galaxies provide one of the most compelling pieces of evidence for dark matter. Astronomers can measure the speeds of stars and gas clouds in a galaxy by observing the Doppler shift of their light. The Doppler shift is the change in the frequency of light due to the motion of the source relative to the observer. If a galaxy's mass were concentrated in its visible stars and gas, we would expect the rotational speeds of stars to decrease with increasing distance from the galactic center. However, observations show that the rotational speeds of stars remain relatively constant even at large distances from the center. This unexpected behavior suggests that the visible matter is embedded in a much larger halo of invisible matter that extends far beyond the visible galaxy. This halo of dark matter provides the additional gravitational pull needed to keep the outer stars orbiting at their observed speeds. The rotational speeds of galaxies, therefore, provide a powerful tool for mapping the distribution of dark matter in the universe. By studying these cosmic speedometers, astronomers can infer the presence and distribution of dark matter, even though it cannot be directly observed. While the gravitational effects of dark matter are undeniable, its fundamental nature remains one of the biggest mysteries in modern physics. We know that dark matter is not made of the ordinary matter known as baryonic matter. Baryonic matter is composed of protons, neutrons, and electrons, the building blocks of atoms. Dark matter does not interact with light, meaning it does not emit, absorb, or reflect light. This makes it invisible to telescopes and other instruments that rely on electromagnetic radiation. Scientists have proposed several candidates for what dark matter could be. One leading candidate is a class of hypothetical particles known as weakly interacting massive particles, or WIMPs. WIMPs are thought to be heavy, slow-moving particles that interact very weakly with ordinary matter. Other candidates include axions, sterile neutrinos, and even more exotic possibilities. Despite decades of searching, however, no experiment has yet definitively detected dark matter particles. Section 5. Dark energy. The universe's accelerating expansion. In the late 1990s, astronomers discovered the universe's expansion was accelerating. They studied distant supernovae to measure this expansion. Surprisingly, the expansion wasn't slowing down, but accelerating. This discovery earned the 2011 Nobel Prize in Physics. The mysterious force driving this is known as dark energy. Dark energy makes up about 70% of the universe's energy. Its existence has profound implications for the universe's fate. Section 6. The cosmological constant, a flawed genius. One of the most intriguing explanations for dark energy harks back to Albert Einstein and his theory of general relativity. Einstein introduced a term into his equations called the cosmological constant, denoted by the Greek letter lambda. He initially added it to counteract the attractive force of gravity and maintain a static universe, a belief widely held at the time. However, when Edwin Hubble's observations revealed that the universe was expanding, Einstein famously called the cosmological constant his biggest blunder. Ironically, the cosmological constant has experienced a resurgence in modern cosmology as a possible explanation for dark energy. In the context of dark energy, the cosmological constant represents a constant energy density that permeates all of space. This energy density would create a repulsive gravitational effect, counteracting the attractive force of gravity and driving the accelerated expansion of the universe. While the cosmological constant fits well with current observations, it raises fundamental questions about the nature of vacuum energy and why it has the specific value that it does. The cosmological constant remains a topic of active research and debate among cosmologists. Section 7. Probing the darkness. Unraveling the mysteries. Unraveling the mysteries of dark matter and dark energy requires a multifaceted approach, combining observations from telescopes and other instruments with theoretical modeling and particle physics experiments. Astronomers are using a variety of techniques to study the distribution and properties of dark matter. These techniques include mapping the cosmic web through gravitational lensing, studying the rotation curves of galaxies, and analyzing the cosmic microwave background radiation, the afterglow of the Big Bang. Particle physicists are searching for dark matter particles directly using underground detectors and particle accelerators like the Large Hadron Collider, or LHC. Cosmologists are developing new theoretical models and simulations to explain the properties of dark energy and its effects on the evolution of the universe. They are also studying the properties of distant supernovae, baryon acoustic oscillations, and other cosmological probes to constrain the parameters of dark energy models. The study of dark matter and dark energy is a vibrant and rapidly evolving field. New observations and theoretical breakthroughs are constantly refining our understanding of these enigmatic entities and their role in shaping the universe we live in. Section 8. The quest for dark matter particle hunters on the move. The search for dark matter particles is one of the most challenging and exciting frontiers in particle physics. Because dark matter interacts so weakly with ordinary matter, detecting it directly requires extremely sensitive experiments that can pick up the faintest of signals. One approach is to build detectors deep underground, shielded from cosmic rays and other sources of background noise. These detectors are designed to look for the tiny flashes of light or electric charge that would be produced if a dark matter particle collided with an atom in the detector material. Another approach is to use particle accelerators like the LHC to smash protons together at incredibly high energies. These collisions can create new particles, some of which may be dark matter particles. By analyzing the debris from these collisions, physicists hope to find evidence for the existence and properties of dark matter. Despite decades of searching, however, no experiment has yet definitively detected dark matter particles. The quest continues, with new generations of detectors and experiments pushing the limits of sensitivity and exploring new regions of parameter space. Section 9. Mapping the cosmos, unveiling dark energy's secrets. While the search for dark matter focuses on detecting its elusive particles, the study of dark energy takes a more cosmological approach. Cosmologists are using a variety of observations to map the distribution of matter and energy in the universe and to study the expansion history of the universe. One powerful technique is to observe distant supernovae. Type Ia supernovae, in particular, are extremely bright and have very consistent intrinsic luminosities. This makes them excellent standard candles for measuring cosmic distances. By measuring the redshifts and apparent brightnesses of distant supernovae, cosmologists can reconstruct the expansion history of the universe and constrain the properties of dark energy. Other cosmological probes include baryon acoustic oscillations, the large-scale clustering of galaxies, and the cosmic microwave background radiation. These observations provide complementary information about the universe's expansion history, the growth of cosmic structures, and the properties of dark energy. By combining these observations with theoretical models, cosmologists are working to unravel the mysteries of dark energy and its role in shaping the fate of the universe. Section 10. The future of cosmology, dark matter and dark energy's enduring allure. The mysteries of dark matter and dark energy captivate scientists and the public alike. These entities hold the key to understanding the universe's fundamental constituents and fate. New telescopes and experiments promise unprecedented sensitivity and resolution. The LSST will create the largest and deepest map of the universe. These projects may revolutionize our understanding of dark matter and dark energy. The quest to understand the dark sector is a journey into the unknown.